All right, let's get started. I'm going to get the sign-in sheet passed around. Okay, so just a quick update on grades and status and whatnot. So your attendance grades are up to date on Blackboard. Your homework 7 has been graded and returned. I am not done grading your exam 2. My goal is to try and get that back to you on Monday. A few other updates because we're actually starting to get down to the wire. The semester's winding down. So I figured I would give you a little bit of an update as the semester closes. So first off, actually, I think that's a typo. That's the 30th. Whoops. It is the 30th, right? Yeah. No, yeah, you're like, oh, we'll get it done earlier, yeah. I don't know about all that. Okay, all right. So one thing, I'm not sure if you all are aware, we didn't mention this on Monday, but we've hired a new administrative assistant in the division. Her name's Lee McDonald. So if you start getting emails from her, that's not junk mail. That's probably going to be scholarships or student meetings or all that stuff. So just have that name, keep that in the back of your head because, you'll start getting messages from her. Let's look at the homework schedule. So we only have 2 homework assignments. What?
I hope Miss McDonald's husband's name is Robert.
Oh, okay. All right. Let's look at our homework assignments. I've gone ahead and assigned homework 8 today on development length. We'll be covering that today, Monday, probably a little bit into Wednesday, but it's not a very long topic, so you should have plenty of time to finish that by next Monday. It's also not a really long assignment because once you know how to do a development length calc, they're all fairly similar. Afterwards, I'll give you all homework 9 on columns and beam columns. That's going to be a little bit of a beefier assignment, but that's our last one. After that, we are done. And just the light at the end of the tunnel, exam 3, our final exam's on Monday of finals week, so we get it done early. It's pretty much right at class time, 10 to 12. Our exam review will be the last lecture of the semester. So, sound good? Any questions? All right. So we kind of started to discuss development length right before we got into exam territory last week. So I kind of want to bring that up and get that discussed a little more explicitly. So if you recall, this is sort of where our discussion stopped last time. We were looking at a beam, and this is looking at it in plan view. And for instance, this beam has 6 bars of reinforcement. And one of the things we were saying is, well, you actually don't really need those 6 bars throughout the entire length because, M max, your maximum bending moment, only occurs at midspan. So you really only need those bars at midspan. So why do you continue those bars all the way along the length of the beam? And the answer is because of bond strength. We talked last time about that analogy, with the tug of war. If you and I are engaged in tug of war and I'm allowed to hold all of the rope and you're only allowed to hold, a little bit of it, it doesn't matter how strong you are or strong I am, because you're not able to get a strong grip on that rope, you're not going to win. You're not able to develop your full strength. So you need a little bit of slack, if you will, in that situation in order to have a fighting chance. Well, it's kind of the same thing with rebar in concrete. When we've done a lot of our calculations, like for instance with beams, we assume tensile steel reaches its yield strength, right? So the tensile force generated in a beam is just the area of steel times Fy. Well, that is based on the assumption that rebar is embedded far enough into the concrete so that we can develop its full capacity. So what we're going to try and do over the next few days is try and ask the question, well, how far is that? What is a particular piece of rebar's development length? How far must that piece of rebar be embedded in order to develop its full capacity? So, it kind of makes sense when you look at rebar. I mean, obviously if you've ever seen it, rebar has grooves, it has ribs. So the farther that you embed that rebar into a given concrete element, if it's an adjacent beam, if it's a column, if it's a wall, what have you, the farther you embed that in, the more ribs come into contact with concrete. The more ribs come into contact with concrete, the more area that rebar has for grip. So it should stand to reason that the longer your development length, the more capacity that you would get out of that bar. Now, there is a point when you can yank on that bar all day long and you're going to fail the bar before you fail the concrete, and that's where development length comes into play. Before we get into the equation, the model that we use to predict development length, I want to talk a little bit about bond failures. So what I mean by a bond failure is this. If you have a piece of rebar embedded into some concrete, like let's say this is a big concrete wall and I have a piece of rebar embedded into it and I start yanking it, okay? Now I could just yield the bar and fail the bar, or I could start to crack the adjacent concrete. Well, the way that concrete fails in that type of mode is you kind of get these cracks that spread out in a radial fashion away from the bar. So for instance, if I have like let me sort of just draw over here to kind of illustrate what's going on. Let's say I have, some sort of beam, some sort of concrete beam, and I have a piece of rebar sticking out of it right here. Okay, so I grab that piece of rebar and I start pulling on it like this. If the bar is strong enough to resist that load, and let's say I start cracking the concrete, what will happen is that concrete will start to begin to sort of crack out like this, and it sort of cracks out in a circular radial pattern. Okay, and that cracking will continue until it hits one of three things. Till it hits, this edge, till it hits this edge, or if you have, let's say, another bar over here and you're yanking on it as well, you've got cracks splitting out here, cracks splitting out here, so on and so forth, maybe until those two cracks meet. Does that make sense? So it just depends on your dimensions. The reason why I bring this up now is because you're going to see a term in the development length equation called C sub B, and C sub B is essentially the minimum of those three distances, and that's going to be your worst case scenario. So when you see that, you go, oh, okay, now I see where that's coming from. Yes, sir?
Does this have to do with the Bridges when
That's a good question. First off, I'll say this. So the investigation is ongoing, so I don't really know specifically what caused that failure. If it's what you say it is, that it was happening during tensioning, I don't think that's the same thing here. The reason why is because if you actually look at that structure was a pre-stressed concrete truss. Okay. Now, first off, that's a unique one in and of itself, because that means you've got elements in compression and elements in tension. And we know by now that concrete is a material that doesn't respond very well to tension, right? If that happened, it's possible that when you're applying pre-stress, you're jacking your cables in one location, it's a truss. You put force in one member, you're going to cause forces all over. So if that's the case, that's probably what happened, is that you're putting force here and it's causing forces in adjacent members that might have caused it to fail. But then again, that might not have been what happened. It could have been a whole string of other things. There could have been initial cracks in the member from day one. It could have been misaligned on the supports. There's a whole host of things, and there's going to be a months-long investigation and lawyers and hearings, and we're not going to probably know the final answer to specifically what happened for a good year, maybe even longer, so because that's going to be a thing for a while. So, but to go back to your question, that's probably not what happened here. Does that make sense? Everybody else okay with that? Again, if you got any questions, please, feel free. Okay. So again, just to emphasize, and I'm going back to this example that I think I showed you all earlier. For instance, if you have a cantilevered beam, we know now that if you have a cantilevered beam, the rebar goes in the top, right? Top region is seeing compression. But if we just had the rebar in the top and we stopped it right here, just think about this from a physics perspective. You take that beam, you're applying vertical load, you're bending that element. That element's wanting to bend down like this. If that rebar isn't tied back into that adjacent element, this is just going to fall right over. That piece of rebar has to be embedded into that adjacent element some specific amount. specifically, it needs to be embedded far enough so that we can reach Fy in the steel. Because, when we design, we assume that we can reach Fy. That length is called the development length, and that's what we're going to try and compute. Now, you see this equation and you go, that just looks nasty. That just looks horrible. Why are you doing this to us, Dr. Mike? This is ridiculous. First off, while this equation looks nasty, you're going to find that development length calcs are actually among some of the fastest calculations that we perform. You think, oh, I'll just design a simply supported beam, with an unknown cross-section 8 pages later, right? But this one isn't really that bad. It's pretty straightforward. There's a couple things I want to point out about it. Number one, this is a highly empirical expression. You are not going to break out some differential equations and some mechanics and solve for this. That's not where this comes from. This is highly empirical. You're going down to the lab, testing beams, testing columns, figuring out, taking measurements, and then curve fitting an equation that best represents that data as closely as possible. So this is highly empirical. Number two, there's a lot of parameters here that you should be familiar with. I mean, everybody here knows Fy. We see a square root of Fc prime, right? So we know to put in PSI, get out PSI. We see lambda. Lambda's the same as it's been for modulus of rupture and other computations. D sub B, that's just the bar diameter. So if we're looking at, number 7 bars, what's the diameter of a number 7? Pop quiz, anybody remember that? 7 divided by 8, right? Remember anything up to a number 8, just take the number and divide it by 8. There we go. Everybody's remembering this stuff. That's good. Now, there are some new parameters, specifically these psi factors. So there's a psi t, psi e, and a psi s factor. One of the things you'll find in that when you go through this, the default value for a lot of these factors is 1. So the default factor for the bar coding factor is 1. What I want you to do is sort of think about this. So if the default value is 1, let me ask you a question. If that value is larger than 1, let's say the default value is 1, but for your case the value is 1.2, will that serve to increase your development length or decrease your development length? Increase. So usually if a value is larger than 1, it's indicating sort of a not so desirable scenario in terms of development length. And I think that'll make sense here in a second. A quick example is, how many of you have ever seen, you got rebar, but how many of you have ever seen epoxy-coated rebar? That rebar with that green sort of rubber coating. Well, that rebar is a little more slippery, right? So if you were using epoxy-coated rebar, do you think your development length would have to be longer or shorter? Longer. So if you have epoxy-coated bars, do you think your psi e value is higher than 1 or lower than 1? Higher than 1. So you're going to see that here in a second, and I think you'll see where this is coming from. Okay. So let's take each of these factors one at a time, and I think you're going to find when you start going through this that this is a lot of it's just look up and plug and chug. It's really not that difficult. Yes, sir? No. You're talking about, are you saying the strength between the epoxy and the rebar? No. But really from a capacity standpoint, we really don't care. The only reason that we're putting epoxy-coated bars is for corrosion. So we don't really worry. That's not really a big deal. As long as that concrete is completely encasing it, it's all going to act as one composite unit anyways. That's a good question, though. Any other questions? All right. So let's take these factors one at a time, and let's make sure we sort of understand where these are coming from. So let's start off with this psi t. Okay? This is called a reinforcement location factor. Yes?
This may be a dumb question, but I think I kind of missed it. What is development length?
So what development length is how far a piece of how far a particular bar needs to be embedded in order to develop its full capacity. In other words, if I yank on that, I'm going to be able to reach Fy of the steel. That's what it is in a nutshell. Does that make sense?
Connection between two beams? Or like beam to a column?
Okay. I had like 6 questions all at once there. Okay.
So the rebar development length is how far from the end of
Yes, yes. So for instance, in this situation, the development length would be how far I would need to embed this particular bar in order to develop its full capacity. That's why we call it development length, so that we can develop the full capacity of the rebar. What were you going to say? Because you sort of said something too. So, okay, that's a good question. Let me. That's a good question. So let me go back to this. Do you remember this example that we did when we started cutting off the bars where we needed to develop the full capacity? Well, the problem with this is we're cutting this bar off right here, but what we would need to do is take this bar and extend it past, one development length. So what we end up doing from a practical scenario is just doing this anyway. It's just to keep it simple. Does that make sense? All right. Anybody else? This is good stuff. Into the adjacent element, yes. So another really common example is imagine if you're designing a retaining wall. Okay, so imagine taking this and sort of sitting it up. Okay, now in geotech you're learning about the earth pressures and the overturning moments and things like that on the wall. But one of the things that what we have to handle is this. Is what we have to say is this. We can determine the moments on the wall just using statics. But what our job would be as reinforced concrete designers is how far does this bar need to be embedded, let's say, into the foundation in order to keep that wall upright? Does that make sense? Imagine if we're taking this and sort of tipping it up like that. So this is our retaining wall, and let's say the soil's back here. Does that make sense? What's that? Pretty much, yeah. Pretty much, yeah.
That would be like, say you got a concrete cantilever retaining wall, deep into the soil.
Well, no, you would have a concrete base under it. So it's how far does that bar need to extend into that base?
Oh, okay.
Does that make sense?
The middle part of it to the...
Yes. Does that make sense, everybody else? This is good stuff. Now, let's take these factors one at a time because I want you to understand what these factors are. So this psi sub t is what's called a reinforcement location factor. A lot of structural engineers, we call it the top bar factor, hence the psi sub t. And here's the reason why this factor is present. I'm going to go back to materials lab last semester. Y'all remember casting cylinders and casting beam specimens and whatnot? Now, oh, you remember. Now, if you don't consolidate that cylinder well enough, if you don't rod it or give it the old tappa on the side, what happens to the cylinder? What do you get in the cylinder? Voids, right? Okay, so not only do you get voids, let me also ask you this. Where are you more likely to get those voids? On the bottom of the cylinder or the top of the cylinder? The top. Why would you be more likely to get voids on the top as opposed to the bottom? Exactly, it's gravity. That concrete is going to want to settle towards the bottom, right? So if you start going down to the lab and start testing a bunch of beams, columns, walls, etc., what you find is that the bars that are on the top of the beam, they don't tend to bond as well as the bars on the bottom. Because of the effects of gravity and consolidation and settlement, you tend to get better bond on bars down here than you do bars up here. So from a development length situation, if you have bottom bars, the bars that are on the bottom of the beam, we take our psi t factor to be 1. That's the default. Okay? But anytime you have bars on the top, specifically bars where this dimension is more than 12 inches, we say, okay, our psi t factor needs to be bumped up to 1.3. So anytime you're dealing with bars that are on the top, you have to up your development length about 30%. Does that make sense? Am I okay with that? Okay. Now let's look at the next factor. Let's look at psi sub e. So psi sub e is our bar coating factor, and we call it psi sub e because we're primarily talking about epoxy-coated rebar. So first off, the default value is 1, and that default value relates to regular old uncoated bars. So if you're ever dealing with uncoated bars, your bar coating factor is always going to be 1. If you're ever dealing with epoxy-coated bars, it jumps up. Now, it jumps up dependent upon what your cover is. Y'all remember what cover is, right? How far the rebar is to the edge of the concrete, or how far in this case, how far the bars are from each other. If you have, first off, if you have epoxy-coated bars in general, your ACI factor is going to be at least 1.2. However, if you've got epoxy-coated bars and you've got really tight bar spacing or really low cover, specifically if your cover is less than 3 times the bar diameter or your spacing is less than 6 bar diameter, not only do you have epoxy to deal with, but you don't have much concrete surrounding those bars. So you got to bump your development length up significantly. So it's either 1.2 or 1.5 dependent upon your dimensions. Now, just as a rule, what if you're designing a, let's say this is a highway bridge out in, Miami, and you're worried about salt water and you're worried about salt conditions, so you have to use epoxy-coated bars, and you start computing development length, and you find that you need like 72 inches of development length, and you just don't have 72 inches of development length. What do you do? Well, there's a couple of different options. One thing that you could use is galvanized rebar. You actually take the bar and just hot dip galvanize it. Now, it's a little more expensive, but it pretty much has the same surface conditions as epoxy-coated bar, so you can take your ACI factor to be 1. So that might be an option. And that's one of the things that we're going to find in this development length discussion is that, it's one big question. It's like, what if you don't have enough room? What if you need 72 inches of embedment and you don't have 72 inches? There's a lot of different adjustments that you can make and a lot of different tweaks that you can make to your design in order to affect that. So it's just that'll be an evolving discussion throughout this concept. Yes, sir.
Are you allowed to use the epoxy? Here's my thought with the epoxy going if it's going into another wall and folding. Couldn't the epoxy pull off almost?
It could, but
Is it like are there restrictions? I guess I should say, like in terms of like if it were to pull.
I guess, but I'll say this. Normally, in those types of situations, not only are you using epoxy-coated bars, but you are providing more than enough cover to where that probably wouldn't happen. You end up having oversized elements anyways. Like if you're using epoxy-coated bars, you're probably using like 6 inches of cover, 4.5 inches of cover. You got these Mambo reinforced concrete elements that aren't going to have a problem anyways. That sound good? All right. This one's really wild. This one's kind of interesting. All right. I'm gonna throw you for a loop a little bit. Okay. Remember when we were designing reinforced concrete beams and we said, okay, you've got you need an area of steel required of like 3.4 square inches, right? You know that because there's only so many rebars, only so many multiples of rebar that fit within a given beam, we've set up until now use the minimum amount of bars possible, right? Okay, so I'm going to throw a really out there example to make my point. But let's say for a given beam design option, you could use one number 18 or, I don't know, 20 number 3s. It sounds silly, but let's say that for the sake of discussion, that those two options have the exact same cross-sectional area, right? Let's just say for sake of discussion. Now, like I said, I'm throwing really out there examples, but I want to make my point here. While they have the exact same cross-sectional area, what they don't have is the same surface area, right? Okay, so the advantage for the 20 number 3s is that the 20 number 3s have significantly more surface area than the one number 18. So think about that. If you have more surface area, you have more area in contact with the concrete. So you do not need as much development length because more of that concrete is in contact with the steel. So that is a wild example, but here's one that's not so wild. Let's say you're doing a beam design and you've got an option between, let's say, 5 number 7s or 6 number 6s. Well, if you use bars that are number 6 and smaller, your psi factor drops down 20%. So if you're running out of room, maybe use a little bit of a smaller bar size and you can drop your development length 20%. See, now it's not as simple as just, the lowest number of bars always works. You got to put your thinking cap on and think about the concept. Does that make sense? Does anybody have any questions about that? Again, the number 18s or number 3s, that's a wild example, but number 7s and number 6s, that's not so wild. That's pretty well within the realm of reality. Okay? It just comes from testing. It just comes from going down to the lab and testing. I mean, it's just the data. So, and honestly, if you want to get crazy with it, if we really wanted to get technical, there's probably a way that we can map an equation for psi sub s. Like say, here's the bar diameter, and let's map the data. But then, there's a point when it's getting too complicated for government work. Just pick a value and go with it. So, I'm serious. I mean, what's that? Really? I was saying, hold on. All right. Okay. There was a couple other parameters that are a little new. One of these values is C sub B. Okay. So there's a denominator on the development length expression that's the following equation. It's C sub B plus KTR over dB. Now these parameters all serve to have an intended function. Now let me go back to the development length equation because I want to explain something. Let's look at C sub B and let's look at KTR. Okay? If those values get larger, what happens to your development length? Just think about this mathematically. If CB or KTR gets bigger and bigger, what happens to LD? Smaller. Okay? So think about that. Those values go up, development length gets smaller. Now let's see what they are. Okay? C sub B is that distance I was telling you about in terms of cracking. Okay? So it's one of 3 distances. It's either the distance from a given bar to this edge, a given bar to this edge, or given bar halfway over to the next one. Because that's how those crack patterns are going to form. So the idea is the longer that distance is, the more concrete you got to fail, right? So think, as CB goes up, you would think that your bond gets stronger, so your development length should go down. Make sense? So that's what KTR, or that's what CB is doing. As that value goes up, that goes down. Now, because this is empirical, that fraction that you see right here, this fraction, this ratio, this fraction is limited to 2.5. So you can start plugging in values and get a value that's like 2.786. You cut that off at 2.5. 2.5 is the maximum for that fraction. Don't worry, we'll go through an example and show you where that plays in. So that's what C sub B is. What about this KTR? KTR is basically a measure of how your transverse reinforcement is helping your development length. And what I mean by transverse reinforcement for beams, basically stirrups. Okay? What do you think the stirrups are doing for development length? Now, obviously, we're putting stirrups in the beam to resist shear, but what are they doing for development length? What do you think they're doing to that concrete? They're holding it together, right? More of those stirrups, the more stirrups that you have, they're going to hold that development length, they're going to hold that core of that concrete together. They're going to serve as sort of a confining agent for that concrete. So, I mean, think about it like this. Imagine this beam, but you have a bunch of stirrups, around those bars. Those stirrups are going to confine that concrete, and by confining that concrete, the more confinement you have, that's going to give you a benefit on development length, right? That makes sense? So in order to compute that, it's 40, and then we take the area of transverse reinforcement, which that's basically just AV. That's just your shear reinforcement. We have S, which is the center-to-center spacing, which is basically just your stirrup spacing, and then N is however many bars you have in a single layer. So if we had a beam like this, N would be 3. The reason why the terms are a little different is what if we're not looking at a beam? What if we're looking at a column or slab or something like that. So that's why the names are a little different. But in the end, we're going to keep our discussion for beams, and then you can translate that to columns and walls quite easily. Yes, sir?
Your ATR, is that just in the cross section, or is it?
That's AV. Remember how you had like a number 3 U-shaped stirrup? So well, no. If you had a U-shaped stirrup, it'd be 2 number 3s. Yes. No, because that's where the S comes into play. Sound good? Everybody good on that? All right. Couple final notes, and then don't worry, we'll get into an example. So if you feel like I've just thrown details like crazy at you, don't worry, we're going to soften that a bit with a few examples. So a couple notes when computing development length. Whenever you compute this product, we always limit that product to 1.7. Again, that just comes from this empirical expression. If you start plugging in values, again, this is an empirical relationship, and it fits the data quite well, but it has limits, So you have to make sure that you're reining in this expression to predict a value that makes sense. Another thing, and this one's really interesting. So let's go back to beam design. So you all remember, let's say you do a calc and you get an area of steel required of like 3.4 square inches. Are you providing exactly 3.4 square inches? Probably not, because there's only so many bars at so many multiples. You'll probably end up providing a little bit more, right? You're providing like 3.6, 3.8, just based on however many bars we got at so many intervals. So what ACI allows you to do is they actually allow you to cut that down, that development length down, by that ratio. A simple way of thinking about that is this. Let's say you do the math and you require 3 square inches of steel, but you're crazy and you put 6 square inches of steel in it. You double the amount of steel. Well, the idea is, well, if you put twice the amount of steel than is necessary, you only need half the amount of the development length. You see what I mean? So that gets a pretty nice advantage for development length, and it makes really good sense conceptually if you think about it. Does that sound good? I know it's a lot of details, but don't worry, we'll take it one step at a time. Everybody good? All right. Let's look at computing some development length. Specifically, we're going to try and compute development length for these 3 bars here on the bottom. So I got 3 number 8s on the bottom. We're going to do this problem 2 different times. We're going to start off using a KTR value of 0, and then we're going to compute KTR and see how that affects development length. And that's one of the things that we're going to do throughout this concept is we're going to start off with like a really, really simple development length computation, and then we're going to see, can we take that development length and start crunching it down a bit by using our various adjustments. All right, so we've got 3 uncoded number 8 bars, assuming KTR is 0, KTR is computed. We're going to use 3 KSI normal weight concrete, 60 KSI steel, and here are the dimensions. I'm actually going to be lazy and copy this image over to our notebook. Oh. Oh, my goodness. And this is what, 16A? Okay. So let's start off, let's just list some parameters that we know. So we know that some material parameters. Okay, so we've got FC prime is 3 KSI. We've got, well, lambda is 1, and we've got FY is 60 KSI. All right. Now let's see if y'all remember this. So this is a what are the size of the bars? We got number 8s. So a number 8 bar. What's the diameter of that bar? 1 inch, right? Now what if this was a number 9 bar, number 10 bar, number 11 bar? What's the diameter? Look it up, right? It's in the slides. So just think about that. I might make you look that up at some point. All right. So first thing I'm going to do is I'm going to start listing my adjustment factors. Hold on. All right. So there's 3 of them that we need to consider for this model. Let's start off with psi t. Now that's our top bar factor. What's that going to be for this problem? It's 1. Why? Because these are bottom bars. Now, just so I'm going to hop back and forth between the slides, but I want to make sure everybody sees this and understands this. So here's our top bar location factor, and any time that this dimension is greater than 12 inches, this is 1.3. Otherwise, this is 1. So pretty much any time that your bars are on the bottom of the beam, so we're looking at these bars here, anytime they're on the bottom, that psi adjustment factor is going to be 1. That's pretty easy, right? Yes, sir.
What if you also have compression steel at the top?
Then you would have a different development length for that compression steel. But let me also say this. Development length for elements in compression is kind of computed differently altogether. It's just a different equation, but it's a little easier. So tension's the hard one. Sound good? Now, what is psi E going to be? 1. Why is that? They're uncoated. Okay. What about psi S? What's that going to be? 1. Why is that the case? Because they're number 8 bars and they're bigger than number 6s. That's pretty simple, right? Now, before I move on, I just want to make a little note here. What is psi t times psi, oh goodness, times psi e? What is that? 1. That has to be less than or equal to 1.7, so that's good. If it was bigger, then we would just replace those 2 quantities with 1.7 in our development line, just so everybody's aware of that. Sound good? You would just, in the equation, take psi t and psi e, take both of them out and just put in 1.7. Like that product is 1.7. Okay. Now, for this example, we're going to take KTR to be 0. Now, KTR is actually measured in inches, so that'll be 0 inches. But let's look at C sub B. Let's see if we can compute that. All right. So let's see if everybody's paying attention. There's 3 dimensions for C sub B. Okay. There's this dimension. What's that? 2.5. There's this dimension. Now, what's that? 3 inches, because it's 18 inches tall, but the effective depth is 15, so that's 3. And then there's halfway over to the next one, and what's that? 1.5. So which value are we going to use? 1.5. In other words, if I start yanking on these bars, what's more than likely going to happen is they're going to crack sort of like this. See what I mean? Because those cracks are going to extend halfway over to the next one. So we're going to do that in a sec. We're going to take it, like walk before we can run. We're going to do a KTR one here in a quick sec. All right. Everybody okay with this? All right. So the only thing that we have to do in order to investigate this is we say, all right, we have to do one more check. Note, what is CB plus KTR over dB? Well, it's, oh, sorry, that's CB is 1.5 inches. So it's 1.5 inches plus 0 inches divided by 1 inch, and what is that? 1.5. That ratio has to be capped off at 2.5 inches. So, or not 2.5 inches, 2.5. So that's capped off at 2.5. So that's okay. Okay? If it was bigger, we would just use 2.5. Is everybody okay with that? All right. So, development length, just plug and chug. So the development length is, so we have 3 over 40. We have Fy over lambda square root of Fc prime. And then we have psi t, psi e, psi s, and then CB plus KTR over dB times dB. Everybody okay with that? I just pulled that straight from the code. So plug and chug. And what I like to do is let's just put all the values on the top and all the values on the bottom and just do one big fraction. That's just how it was written in the code. That's what the code folks like to do. It must be in government work. I don't know. I need a marker or a mic or something. All right. So we have Fy is 60 KSI. Anybody got a problem with that? It needs to be in PSI because the square root of FC prime is in PSI. So write the little k, the little s, the little I. Put the dot on the I. And then you will see that there's a problem. Okay? So we have 3, we have Fy, we have psi t, psi e, psi s. They're all 1. So obviously, you don't need to do that in your calculator, but I'm doing it here just to see where the values are coming from. D sub b is 1 inch. And then on the bottom, we have 40. We have 1 for lambda. We have the square root of 4,000. Or is it 3,000 or 4,000? It's 3,000. 3,000 PSI. And then our ratio, and instead of doing the fraction again, we already computed what that fraction was. That's 1.5. So what does that come out to be? 54.8 inches. So for simplicity, we would say 55 inches. So that bar would need to be embedded to a length of 55 inches, or those 3 bars would be embedded to a length of 55 inches to develop their capacity. That's pretty simple, right? Okay, now let's do this again. It gets kind of repetitive once you do it once, you can do it again. Let's do it again, but let's compute KTR, and let's see what happens. In other words, if we account for the stirrups, what happens to our development length? Do you think it's going to go up or go down?
Go down.
Should go down. Let's see if that happens. So
Is that like a reasonable number? That's going to be cantilevers to cerebral decline. Like, you're trying to embed that into something that's a long list.
no, it is, and you're going to see how throughout these examples we can take that number and really chip it down a bit. And there is another whole big world that we're not even talking about. One of the ways that you could substantially decrease the development length of a bar is to bend it. To actually bend the bar into a hook. Because you're embedding a hook, now the concrete sort of has something to hold on to. Instead of, if I was holding, a rope or holding somebody's hand like this, what if I'm sort of hooking it in? Now I've got a much stronger bond, that development length could go down. There's a whole bunch of strategies that you can use to take this number and chip away at it. But we're going to take them one at a time. So.
Wouldn't that change your CCP though? So I mean, if you hook it, you got to hook it in a direction. So like down, one and two.
Well, I'm talking about sort of in 3 dimensions, like if the bars were going like this, I'm talking about like hooking it up like that.
Oh, okay.
Yeah. Does that make sense?
Yeah.
My perspective's probably horrible, but
No.
okay. Not an archmanger. Okay, all right. We'll do this other one and then we'll call it. So now let's compute KTR and let's see what happens. Okay, let's compute KTR. So for this one. So KTR, we compute that as 40 times the transverse reinforcement over S times N. Okay? So we have 40. All right? Now, ATR is basically our shear reinforcement. Now, for our beam, what do we have? We have number 3 U-shaped stirrups. So what's AV? 0.22. So this is going to be 0.22 inches squared over S. How far apart are these stirrups spaced? 8 inches. And then N is the number of longitudinal bars per layer. How many longitudinal bars do we have per layer? 3. 1, 2, 3. So that's 3. So plug and chug, and what do we get here? Inches, right? All right, let me rewrite that. 0.367 inches. Everybody good on that? So now what I'm going to do is I'm going to say note. Now let's compute that ratio again. So C sub B plus KTR over DB is 1.5 inches plus 0.367 inches over 1 inch. So that's what? 1.867? Is that okay? It's less than 2.5. So now we can recompute our development length. So therefore, LD is 3 over 40 Fy over lambda square root of FC prime. And you all know the rest. You all know the drill. Yeah, if you didn't know anything about the stirrup layout, I would say 0. But if you know it, go ahead and do it. No. What, again, like when we're done with everything in class, like our lecture today, lecture Monday, lecture Wednesday, I don't expect you to do the same problem like 6 times, but I'm taking it slowly so that you understand, okay, now I understand this adjustment, that adjustment, that adjustment. So when you do it once, you can do it all. So.
For this, did we just take 55, multiply by 1.5, and divide by 1.867?
You could do that. You got enough time to plug this in. I'm not going to rewrite the values, though. You all can do that. Well, you can do that. Oh. Stay away from, what is it, snails. Stay away from them. The snail, because salt on the snail, right? It's not good. Stay away from them.
I got 44.0.
My goodness. It's Friday. That's what it is, right? So did everybody else get 44 inches? Exactly. See, okay, so hold on. So therefore, let's go ahead and just write this out. So LD is 44 inches, and let's look at that. So that was one adjustment, and we cut the development length down by like 20%. So that's one point that I want to make. You're like, okay, well, what if you don't have the room? One of the big things is, okay, let's go through all these adjustments first, because that was just one adjustment. We cut it down almost a foot. We've got area of steel required adjustments to do. We can start playing around with bar sizes. We can use hooks. There's a lot of different things you can do. I want you to be aware of that, okay? Sound good? All right. Hold on real quick before everybody leaves. Two things. One, sign-in sheet is I don't know if you saw a couple people come in late. Make sure you sign that. I have some homework assignments for those of you that came in a little late. So hold off before you leave. Other than that, y'all have a great weekend. I'll see you on Monday.